Thank you everyone for joining us for this webinar, Network Design Considerations and Techniques for AV Systems, presented by Thomas Hejnicki. My name is Laura Lawrence and I'm the Global Marketing Director at Harman. Just a few things before we get started. Everyone on the call is muted to keep down noise levels during the webinar. However, there is a Q&A function where you can submit questions to the presenter and he'll try to answer as many questions as possible at the end. This webinar is being recorded and the link will be made available a few days after the presentation. We do have a number of other webinars taking place over the next few months for audio, lighting, video, and control, and we'd like to encourage you to take a look at the different webinars in our Learning Sessions workshop series on pro.harman.com. We're adding new sessions daily and have over 20 sessions scheduled for August and September, so watch for those on the calendar. And now I'd like to introduce you to Thomas Hejnicki, the presenter for today's webinar. Thomas has 30 years of experience designing and integrating audio systems for touring and fixed installations. His interest in digital audio networks started in the late 90s and grew to include fiber optics shortly after. Thomas now holds several patents and a degree in computer information systems. Now I'll pass it over to you, Thomas.
Oh, thank you, Laura. Appreciate that introduction and welcome everybody to this presentation. I look forward to covering some essentials for what I would consider to be important to network design. Over the last 30 years, networking has gone from a very background supportive role to being a mainstay with AV systems, and that now it's just about as seamless of a marriage as one can expect for now. It's truly amazing what we're able to do with technology. So to start the talk, let's consider a definition for network. When I mention network, everybody might think, well, it's a collection of gear, cables, network switches, patch cords, computers, devices, etc., to get information from point A to point B. A collection of devices that are transmitting data across routers and switches, etc. But let's think about it in terms of like a broader or more general sense. That's why I like this slide right here, and I'll use my mouse pointer. So if we look at this, this is a nice depiction of a network. Simply put, a network is a collection of nodes that are interconnected. We could say that this might be a vertex, and we have a series of vertices, and these would be edges. All of these edges represent the paths between the different nodes that comprise our network. So when we think about our network and our network design, we're simply providing and considering paths to connect different nodes. And this vertex might represent as in this one where we have multiple connections, this might be a router or a switch where we have multiple connections and we're both receiving and transmitting information through this node. So what we have to think about is what are the requirements at each node? What is the demand? What I have an input, I have an output. So I need to get an input to an output. So we're going to have a cost and a benefit for sending information or sending anything over this path. Then we're going to have constraints for each one of these paths. We have an expectation that what we input here is going to arrive at its intended location. So our network design has to consider the cost and benefit for sending information from any point to another point or a node to a node over a given path. So optimization of this network is going to look for the shortest path that maintains all of the constraints, that has the lowest cost and the greatest benefit. So as a general definition of a network, we can go ahead and proceed to the next slide here. And we can start with a 30,000-foot view of our considerations for designing any network. And that is initial considerations for the project. We're going to define the project where we have, and this is going to be what I would call the relationship. So we have a relationship with our client or with our maybe a general contractor if we're subcontracting. So I think for everybody, we've all had various experience, whether that's design build, whether that's bid contracts, whether that's maybe you're consulting. What is the relationship? And so we really need to know what our clients' needs are, and we need to be aware of how our results are expected to work in their environment. So I would ask myself questions like, do they have their own independent IT staff? Are they going to be facilitating all of the design for the anticipated network? Are we handing them a gear list, maybe MAC addresses and some requirements? Well, then we need to really hand them over something thorough so that they can suitably design the network if they are handling this. Or if we are kind of working together as a collaborative, then we need to develop common language so that we can communicate effectively and realize the overall objective, which is, once again, the most efficient, cost-effective transmission of data from point to point, and that data is going to be the realization of our client requirements. And that may be audio streams, that might be video, that might be various displays that are set up, so et cetera. We'll just take that as a general. We don't need to get specific into any format of what we're transmitting. We're looking at just simply getting it on and off the highway, so to speak. So then we're looking at project scope, and that's what is the scope of this network. Once again, are we working for perhaps a government contract? Is this an educational facility? How are we setting up an independent network where we're going to be air gapped from any existing technology, or are we expected to interface with existing technology? So we really need all of these questions well defined. So once again, another one, additional considerations, possible constraints. Once again, if we're working with a well-established organization, is there a published specification that they have? Do we have to provide specific materials according to a published spec? Usually that would be part of a bid requirement, but if you're doing this design build, you might need to be aware, or they would hopefully make you aware of any kind of published spec. So just a quick overview of the relationship side of the design. So moving on, the OSI model. Everybody's aware that the OSI model exists, and they're aware of some of the labels, but I'd like to go through it a little bit and see how knowing and having familiarity with the OSI model might be able to actually help us facilitate designs. So once again, OSI model, OSI stands for Open Systems Interconnection, provides a familiar method for this categorization and organization of communication systems into several abstract layers. Essentially, we have many layers in the OSI model. At the very top are going to be our application. This is essentially what we're using. This is our software. This is our end result. This is where the human interface happens, and we then work our way down. We're actually the OSI model. We're going to use more of the TCP/IP or the Ethernet model, where we consider application, presentation, and session to all be one layer called generically the application layer. It's a little bit more straightforward for what we're going to be doing. So with this model, we're going to touch it up near the application layer, and we're going to touch it at the physical layer, but we need to be aware of how all of these different partitions are working as a collection. So as I mentioned before, the OSI model may be a very useful reference for the design of any proposed system, as it's nice to go through your iterative steps, work out and well-define and organize the applications that are anticipated and intended to be functioning on your network. So we know that we need, A, B, and C audio to occur in, zones 1, 2, and 3. We need certain displays to display, this various information. So we'll have that all structured, we'll have that organized, and these are going to be our applications. We're going to know that, are we using Network Manager? Are we using some other actual piece of software that's going to be resonant so that we can align and tune and outfit our intended results and get those results that the client is looking for. So we're going to lay all of that out, and then we're going to kind of drill down the OSI model to determine, well, what's important? What do we need to be aware of for the overall network to be successful? So, with that in mind, we'll go a brief review. So as I mentioned, TCP/IP or the Ethernet model uses the 5 layers in contrast to the OSI model's 7. And this is to be considered standard to address the TCP/IP or Ethernet model for network design. So, as mentioned, we have the top layer, which is all of our services. This is our results, so to speak. And then we're going to go through and look at each layer, and we're going to omit the presentation and session layer. Okay. With, by the way, physical layer being where all of our hardware is going to be. That's our patch cables. Those are our routers. Those are our network switches, etc. The application layer. Once again, here we define the primary purpose of the network. What does the network need to do? So this would be, where are we going to start defining our requirements? We need to have so much bandwidth to get, maybe we're doing audio, maybe we're doing VoIP, maybe we're doing some video. Is that video going to be uncompressed, or are we using H.264? We need to start labeling our features of the network, and we need to see where in that little node and edge diagram are we expecting to relay this information, this data that our applications require, or that our end results require. So we need to know what each of those stems, the cost and the benefit, as I mentioned. How much bandwidth do we need through each segment? How much latency will there be through each segment? Is this a critical application where latency is going to be an issue, or is this maybe an overflow where latency is not that big of a deal? Well, we need to have that well defined. And we can get into other parts of this. As I said, it's an iterative process. We kind of define as much as we can. We drill through the model, and we get as close to the physical layer as we can, and then we iterate through it again, and then refine our results as we go. So we're going to get a good idea of what our bandwidth is at this point. We're going to get a good idea of what latency characteristics we have. And we're going to get a good idea of our general needs and requirements. We're also at this point, we're going to need to be cognizant of the protocols our applications are using. So are we using, this would be where, say we're transmitting some audio. Are we using AVB? Are we using Dante? Are we using CobraNet? Are we using anything else? And once again, maybe this would be a good point to mention. There are certain other transmission schemes, we'll call them, that use Ethernet-like hardware, cabling, etc., but it's not actually Ethernet or network routable, which means we're just using a similar interface, or we're using a similar set of cabling to get information from point A to point B, and these might be our range extenders, etc. Well, we're essentially installing a piece of cable that's getting something from point A to point B, but we're not actually using. If I were to draw that in a diagram, a network diagram, that might be an independent set of nodes with a point A, a point B, an interconnection between those nodes, but it doesn't connect anywhere else in that scheme. It's not going through a switch, and it's not going to be routable. So just wanted to mention that as well, because we do need to be aware of that when we're considering this as part of the installation. It's going to count towards our budget. There's going to be man hours required. There's going to be materials required that we need to put into the budget, specification, etc. So this is at the application layer where we start to define that, and we start to take some accurate notes, and then we're going to drill down. So moving on to the next portion of the OSI model, we'll talk about the transport layer. Transport layer, And here's some examples. TCP, Transmission Control Protocol. Examples of that would be HTTP, your web browsing, etc. And here's a nice chart, we can go through this, of some of the characteristics, features of each TCP versus UDP, User Datagram Protocol, which is UDP. So UDP, as mentioned here, that's going to be your VoIP, that's going to be your streaming services, that's going to be anything that's real-time streaming from a point A to a point B. And the reason that that's done is because, you know, with TCP, the network is looking at loss. We want to confirm that we get absolutely every packet successfully. So we're going to transmit, we're going to confirm, and if we did not receive that packet, we're going to send notification. We want an acknowledgement, please resend, and it's going to resend that packet. So we're going to have, we're going to emphasize quality with our flow control feature. But, you know, by the time we have that happen, say we're 2 hops down and we're you know, a couple of milliseconds. Now, if we need to confirm a packet, acknowledge, let's say, acknowledge that we did not receive that information, it's going to send a request for that information again. We're going to have to retransmit it. Well, now we have a additive property of delay that we're not going to be able to compensate for in real time. So it's a trade-off of whether to use TCP or UDP. If it's important to get reliable information 100%, then we're going to use TCP. If we're doing something live where a click or a blip or something is not going to be noticeable, where if we lose a packet, we lose a couple of bits of information in real time, the cost versus the benefit is going to favor having that bit of loss but having real-time capability. So that's why we have these two different basic categories happening in the transport layer. So we can go through that again through the general description. So UDP, simple, high-speed, low-functionality wrapper that interface applications to the network layer and does little else. TCP, full-featured protocol that allows applications to send data reliably without worrying about network layer issues. And that's, once again, where what I just described, where we're going to have potential for loss and then error correction and compensation, where at our transport layer, you know, we're going to be querying and making sure that we get reliability according to each one of these standards. So one of them, TCP, connection-oriented. Connection must be established. Yes, we need, like I said, we're going to send acknowledgments. We know that this host is going to acknowledge that we now have a connection. And this, by the way, is where we would have ports. So, like if you're familiar with setting up internet mail, IMAP is port 143, or HTTP is port 80, for example. So when you see ports, this is the transport layer. Probably should have mentioned that earlier, but so that's what we're looking at. So applications at this layer, we're looking at sending from port to port. And another analogy that I can add here is, say I'm down in Florida, so we have Port Everglades, for example, and we're going to have, let's say, Caribbean cruises that are all leaving Port Everglades and all returning to Port Everglades. Well, which ship is it? Well, which dock are they located at? I don't know, but they're all at Port Everglades. So that's the port. So when we get down to the next layer, where we're looking at our networking layer, that's where we're going to start adding addresses, and we're going to know specific information about exactly which dock our ship is located. So as an analogy. So getting back to interface application. So TCP, data is sent by the application, no particular structure. We're just making sure that it all gets there and that we acknowledge that it all gets there and there's a specific connection that's going to have that acknowledgement. UDP, we're just going to send the message. It's going to be in discrete packages, but we're just going to send it, but we're not going to acknowledge or not request acknowledgement or confirmation that we've had any issues. So as described here, we're going to have unreliable but best effort delivery without acknowledgement. And then TCP, we're going to have reliable delivery of message. So TCP, we're sending our emails. UDP, we're streaming audio or having VoIP. So right now, we're using UDP. Retransmissions, not performed. So once again, it's potentially lossy. But as we'll see later, there are other features to the TCP IP and UDP schema that help us, and fortunately we have great manufacturers that know about this, and when they come up with the standards, protocols, and start developing their hardware and software, they develop appropriate responses to some of these characteristics. So we can get into that in a little bit when we get to the next few slides. So retransmissions, once again, we're not doing that. This is a real-time situation, so we're gonna continue, because stopping for any brief moment would cause more problems than just persisting forward. So TCP, in contrast, we're gonna make sure that that's managed, that we're gonna have all of our data before we move on. So once again, no features because we're not managing the flow of data for UDP. Flow control, we have adjustability. We have different, I don't want to get too deep into it, but there are ways to adjust flow control within TCP. Overhead, low. Since we're not looking, we're not confirming, we're not worried about reliability, we have low overhead. So what do we gain? We gain speed, we gain performance. So overhead is higher than UDP with TCP, but considering current network technology, it's not bad. It's still low. Transmission speed with UDP, very high. So what we're doing is we're saying that because we're real time, we're going to break our data up into smaller and smaller pieces, send it, and we're going to be very high speed, low latency. So we're really optimized for real time and sending it continuously in real time so that any drop is going to be virtually unnoticeable, or hopefully, and that's the goal. So then with TCP, we're going to be high. We're going to be based upon the overall performance characteristics of the network itself, but not as high as UDP because once again, there's more overhead with all of our potential for reliability. We want that to be reliable. So once again, as I said, we're chopping up our, say for example, we're doing audio, our data quantity is going to be small amounts of data. We're sending quickly, we're sending without delay, and we're hoping to maintain strict timing for that, which we'll get into. TCP, we're sending larger data sizes, and we're doing it a little bit slower due to the overhead and due to the reliability that's inherent within TCP. So that's a quick overview of the transport layer. And it's helpful to know and at least be able to characterize what we have for our applications. Are we using UDP? Are we using TCP? Are we, these are the questions that we're asking. Are we multicasting? Are we unicasting? What do our applications require? And this is necessary not only if we're designing it ourselves, because we have a host of other, once we get into managed switches, we have a host of features that we can activate. For example, differentiated services, which are going to help us manage these various types in the transport layer. And if anybody's familiar with programming a switch, a managed switch for Dante, I'm sure you've heard of diffserv and QoS, so, or quality of service. So let's move on to the network layer. Network layer, this is where we're addressing, we're routing, this is traffic control. This is now where we're getting into, we're in the port and we have 17 ships and we need to make sure that we can, without collision, get them to and from their respective docks, get people on and off, and get their cargo on and off, and get them moving where they need to go. That's a pretty good analogy for that. So this is going to be IP addresses. This is going to be subnet masks, etc. I don't want to get too deep into that because that could be its own talk and own series of questions for techniques to develop and deploy addressing within your network. And essentially, the rules are there really are no rules unless you're working on a team or within a network that has those constraints where they're going to specify that you use these set of addresses in this set of ranges, and you would conform to that, or you would co-develop that in partnership with your team. So how are the devices addressed? Once again, IP addresses, IPv4, IPv6. So we're going to have 4 octets, that's going to be 32 bits in IPv4, which is still, thanks to good routing and virtual IP addresses, et cetera, we're still able to successfully use IPv4, even though we ran out of room quite a while ago. VLANs, LACP, bandwidth, and efficiency. This all happens here. These are where we're going to start considering what is our bandwidth, what does our path look like, how efficient can we make that path. And VLANs and LACP, by the way, is a link aggregation control protocol. I don't know if anybody, I'm mentioning it specifically because I think it's a very useful asset when developing a network. So we'll get into that a little bit more than specific IP configurations, because that gets into organization. And that's really, once you map out your network, well, am I going to organize this into a series of subnets? Am I going to organize it into a series of virtual LANs or VLANs? And then am I going to number accordingly? And am I going to exclude devices from the potential to communicate with other devices? And that's what we're working towards. We're looking towards the most efficient use of bandwidth. We want to maximize that from point to point. So what are the best techniques to use? And numbering scheme, that kind of works itself out once you get all of your partitions created and you can figure out what's most logical and what makes the most sense to your team for how to actually numerically label everything. But once it's numerically labeled and you've assigned the address, then the network layer is capable of sending the information from point to point within that network or subnet. Just as a reminder, you'll need a router to move it from one network to another network. So if you have a one network that is self-contained and complete, and you have another network that is self-contained and complete, we would need a router to move or communicate data from one network to the other. So VLANs are virtual LANs. This is by far one of my favorite, and when I have introduced this to teams historically, they've quickly adopted it, and it's become the go-to. So once again, to get into VLANs, now we're talking about managed switches, and now we need to know that we're into a managed switch category versus an unmanaged switch category. Unmanaged switch, we just expect to plug it in, connect our hosts, all of the nodes to that switch, and that we're going to engage power, and that it's going to effectively do its job without any oversight, no management, nothing needs to be corrected, no settings need to be adjusted, that we're simply connecting this network together, and it's fine on its own with factory default settings. Managed switch means we need to go in and make adjustments and change the characteristics of how that's going to operate. I mentioned before we're going to be looking at, say, for example, for Dante diffserv and QoS, where we're going to be managing that from inside the switch. And to do that, I'm sure anybody that's done it, we have a web interface, log into the default IP address, web browser pops up, and we can now make adjustments to that switch, or we can do it through a command line interface, a CLI, depending on which device you're using. And selection of gear, that'll be in their physical layer, but this is once again why this is an iterative process. So at this stage, we're now determining what we need to successfully transmit from all of our points and route and get data effectively through our network. So VLANs, let's think of this as maybe an envelope. So we have a port, that's one envelope, and now we're going to tuck inside of that another envelope. I might go back a few slides. Right here. So transport layer, let's say that we have this is our port Everglades, where we're going to have this, and this is our address right here. This is going to be in an envelope, and at this we're either segments or we're datagrams. Datagrams for UDP, segments for TCP. So this is going to have a port, and that's how we're going to know which port to send it to in this layer. Okay, when we open up that envelope, so to speak, we now have a packet. We now have packets, and those are in envelopes, and those envelopes are labeled. Each one has a header, so we know who sent the packet, where is the packet going, and then other information. Is that packet belonging to a VLAN? So there will be an identification number that's associated at this level that we can look at, and now our managed switch knows to either include or exclude these packets based upon the set of rules that we're developing to manage that. So those packets would be the VLAN ID. So essentially, we can create a series of virtual LANs. So this is, rather than a physical network where we're having patch cables and host devices and interfaces such as switches and routers, now within one switch, we're able to logically segment or separate that switch into various virtual LANs. So let's say that we have 24 ports and we segment that into 3 8-port VLANs. Well, now I've got a functioning network times 3 in one piece of hardware, logically separated. You can no longer communicate directly. Let's say that that's sockets 1 through 8, 9 through 16, and 17 through 24 respectively. I plug a device into socket 1 and then socket 17, and even I may still be on the same IP address where I'm having this envelope, shared network, other than the VLAN ID. I'm no longer able to communicate. They're now logically isolated and separated. I will now need a router to route between those virtual LANs. So that's how we can separate. So if we have our applications separated into, let's say, audio, maybe control, and a few other additions, maybe we're going to put those on separate VLANs. So I might have, let's say, Dante on one VLAN. I might have control for all of my processing. Maybe I have all of my control that I'm using to control all of my London devices on another VLAN. So I don't need to bother, so to speak, the DSP devices with a bunch of audio information, and I don't need to interrupt my Dante flows with control data information. So now we're just going to zip those up into separate VLANs. And if they do need to speak to one another, there are techniques. Like I said, one of them would be adding a physical router. Another one we can get into when we get to the physical layer would be having a layer 3 switch, which we can get into. So let's go back to stepping through this. So we have our envelope now with our packets, and that has my IP address on it. So that's our 192.168.0.1 or something to that effect. And then once we open the packets, we're going to see frames. Frames are going to be manipulated by the data link layer. Let's go ahead and advance these slides. Data link layer. As I mentioned, okay, so I just happen to have this right here, London configurator. So right here, data link layer is, and if you notice, all of these layers are more boundaries, so to speak, between the actual layers, where the concept is living on the layer. Let's say that we know that the application is on the layer, but all of the protocols that we're using are boundaries. It's going to be reaching into one layer and acting with the layer adjacent to it. So we have the data link layer that is operating in harmony with the network layer and also with the physical layer. So they're kind of the boundaries, if you will, and not the actual, it's the slice in the pie rather than the piece of pie itself. It's one way to think about it. So data layer, we're going to be working on encoding, dividing our packets into bits, establishing the actual physical flow control, and providing management to the connected nodes. This is where we're going to manage. This is not the physical connection of node to node, the actual interface where we turn into logical, where we change logical data and signaling into physical, or logical bits of information into physical signals, would be a better way to put that. So familiar with MAC addresses, this is where our MAC, or media access control, and our actual Ethernet is living at this level. So familiar with MAC addresses, each device with an interface card that's using Ethernet, a NIC or a network interface card, each one is going to be assigned, or should be assigned, a unique MAC address. Anybody familiar with identifying origins through MAC address? There are some nice sites online where you can search by MAC address, and you'll find the prefix, type in the prefixes of the MAC address, and it'll identify which company manufactured that. Every company has this starter, this primary series of hexadecimal. The first 3 segments are going to be an identifier for any manufacturer. So whether that would be Microsoft or Apple, or Harman has several actually with Crown and all of their different segments, have unique MAC address starters. And then this is going to, these last 3 of this hexadecimal code is going to give you the specific card, so, or the specific identifier for that device. And these should be unique for every device. So every manufacturer has their ID, and then the specific device itself has its ID right here. And that's in the MAC address. And using these MAC address, and that's really another way to think about what our layers and what our network switches are doing. Realistically, it's a series of protocols and tables. When we look up, we'll have forwarding tables. So once a switch learns an IP address, it's read the letter. It knows what IP address that is, and now we've opened it up, and it now determines what MAC address this has. So now we're going to set up a table that writes this address. So now we know that IP address is now linked to this. It means this MAC address. So every time now I get a piece of information, another packet comes in. The packet is now directly forwarded to this MAC address through a table, and that's really how our various services in the managed switches are working. We're manipulating different tables that assign different services, different quality of service information. So once again, for example, if we were talking about setting up Dante. Dante is going to use differentiated services. Although we're using UDP, we're going to use quality of service to make sure that we annotate that the information coming from that port and between these IP addresses and now between these MAC addresses is priority. So we're going to make sure that this information now has priority. It's labeled in the table with priority, and it is going to get delivered with priority over everything else. So this might be another reason, depending on your bandwidth requirements. I don't know. Everybody has to determine what applications they need. Can you sacrifice performance of one, perhaps a control feature? Can you sacrifice that to audio having priority? And this might be a reason that's going to motivate you to look into VLANs or having virtual LANs. So now we can segregate that. Once we have a VLAN and that is now dedicated to, say, Dante, for example, Once we have a VLAN that's completely dedicated, there's no reason to differentiate services, and there's no reason to adjust anything, because that is now all Dante all the time exclusively on that VLAN. So, and just wanted to show you that. Let me go back to that. So that's VLANs. Apologize if I'm skipping around a little bit, but since, like I said, we're looking at all of these various boundaries between the layers, these slices in the pie, so to speak, they kind of dip into adjacent layers. So that's why we're going back and forth kind of a little bit. So LACP, link aggregation. In a nutshell, link aggregation control protocol is another feature that allows you to effectively take different sockets on your switch and combine them. So let's say that we have 3 ports that we want to use. They're each 1 gigabit. Once we aggregate that as a group, we now have a 3 gigabit link. And if we do so at the other end on another network switch, we now have an aggregated group between 2 switches that are now aggregating 1 gigabit per port times 3. So now we're sharing a 3 gigabit trunk without having to get into a GBIC or an SFP or some other device. So it's handy, very handy use. Also, it gives you a fail-safe, although the cost. So the benefit is that we can aggregate data and increase our bandwidth. The cost will be the additional cable, and that's a physical cost. Another cost will be if we lose one of those links, well, now we're kind of squelched back to 2 gigabits on that aggregate flow. But we have a built-in redundancy, which is important. So that is, in a nutshell, link aggregation. So a nice way to increase the amount of bandwidth, add redundancy, so that we always have an established link that's active. Although the fail of any one of those aggregated links, would be a reduction in bandwidth, but at least you're still going to have connectivity. So once again, that's a design consideration. So, okay. I think we can back into data link. So MAC addresses. So essentially, at the data link layer beyond the MAC addresses, so that MAC address is what we're using in the table so that we can communicate and know how to compare. We can play post office between the Ethernet or the internet or the network layer and this MAC address. So now we have a table that has an IP, and we have MAC address forwarding tables where we now have learned the IP addresses, and now we can associate them with the MAC addresses, and we can easily switch data from where it needs to go to its intended receiver. So also at this layer, we're going to manage the physical layer. So this has, we want to make sure that we have no collisions. We want to make sure that we have communication happening as per assigned. So if we have full duplex, that we have two-way communication, et cetera. This is all happening at the MAC, I'm sorry, not at the MAC address, but this is all happening at the data link layer. So at layer 2. Moving on, physical layer. So this is everything that is our tangible products. This is all of our cabling. This is our fiber optic. This is our physical network switches. This is everything that is physically tangible. Once we have a set of parameters, once we have well-defined our network scheme, we're now able to define the attributes of our physical layer that's necessary to accomplish our goals. So once again, physical layer encompasses all the hardware, transmission media that comprise a given network. This would be both what I would call guided and unguided media. That would be guided media would be your copper, your Cat 5, 6, et cetera, your fiber optic cable. Unguided would be anything RF. So if you're using satellite, if you're using wireless Wi-Fi, et cetera, that's going to be unguided. So In the physical layer, well, now we have environmental concerns. What's our location? Is it a harsh location? Is there a lot of stray RF? Is there a lot of stray EMI? Are we running motors? What are we doing in this location? If we're doing a paging and background system and we have a lot of machinery nearby, well, we need to consider that. So we need to appropriately shield, we need to appropriately isolate, et cetera. How's our climate? Is this a harsh climate? We need to physically design for that. Are we going to be having vibrations? Are we going to have chemicals in the area? Do we have to consider that with raceways? Do we have to consider temperatures? We have to consider all of these thermal and mechanical properties. Power schemes. So do we have our own protected circuits? Are we just kind of, are we plugging in? Are we working with the electrician? Once again, we get back to the team. Do we have dedicated power? PoE. What's the power scheme for our network? Do we have PoE? Are we going to be providing power to remote devices over the network? Are we going to have a dedicated PoE injector or power supply? Is that going to be local? Do we need to then pick up power for that local PoE injector? We need to advise our team about that. Do we need redundancy? What kind of redundancy? If necessary, is a basic network switch with one internal power supply appropriate, or do we need to have potential a switch with external power supplies in their own PSU chassis, where maybe we have a primary power supply, a secondary power supply, and a third power supply that's caged up, that's exclusive, that's dedicated for PoE. So we're not using the power supplies for the switch capability itself or the switch itself. We're only injecting PoE with the third power supply. That is available. Do we need to then manage that? So how much redundancy do you need? How mission critical is the network? These are all physical considerations. Once again, we'll mention bandwidth. We've kind of, if we have bandwidth limitations and we know that we're not using excessive amount of bandwidth, of course, cost is going, cost is the actual money. So we want to provide, value engineering. We want to reduce costs. So we don't need to install fiber or Cat6 when we really need Cat5 or Cat5e. So we're going to consider, look at all of our bandwidth versus cost. We're going to look at all of our products versus cost. Transmission distances, of course. This is once again where we get into do we need fiber or is copper suitable? If we're inside the same rack, of course, copper is great. We don't want to convert to fiber if we're only running it, 3 feet. Fiber, is practically limitless what you can put down one fiber, and you can certainly do a lot of future proofing by installing fiber. And I would really push for that wherever you can when you're moving considerable distance down a hallway, from an intermediate data closet, from one data closet to the next, from floor to floor, et cetera. I would always try to future proof. And then media type, guided media I've already mentioned. So I think at this point, let's move on. Here's a slide with some helpful resources that you can feel free to consult. The IEEE.org, that is, of course, the IEEE, who have written all of the standards for networking. So those are all of your industry standards. They have publications, articles, et cetera. They're very helpful. If you're familiar with BICSI, Building Industry Consulting Service International, if anybody's RCDD trained or certified, then all of this would be very familiar. The TDMM, very, very useful resource. I refer to and purchased the TCP/IP guide by Charles Kozyrek about 14 years ago when it first came out, and it's been a very, very handy resource for me. Then I've also been referring to another book, which I found, called Business Data Communications and Networking, right here. Feel free to investigate these or any other resources, good information and great companions for any project. So that said, thank you very much. Please feel free to contact me with your any questions or comments that you might have. I appreciate you sticking with me this far. This has been my first presentation, so I definitely appreciate you being here. And here's my email address should you wish to get in contact with me. And thank you again, and I'll hand it back to Laura.
All right, thank you, Thomas. We do have a question that popped up in the Q&A. It's asking, on the physical layer part, if the cross-section area of the cable is a factor, what AWG is standard? Is it 23 or 24?
Well, are we using solid copper? Is this going to, see, I have other questions. 23 is certainly very popular. And once again, you would just look up the wire guide. So they're looking at what American wire gauge cross section is standard. I would say that there are various construction types of cable that is going to suit your needs. So to get into cable requirements, are we a riser cable? Are we a plenum cable? What kind of insulation? How rugged does this need to be? Are we solid? Are we stranded? Does this need to be very flexible? We might be stranded. So if we're lightweight, if we're, we might be using something a little bit thinner. So I would say that 23 solid would be very popular, if that is answering the question. If I missed it, send me an email and send me your specific use, and I'm glad to help you with additional research.
Okay, we have another question. How do I calculate the stack bandwidths between two or more switches when I'm transmitting AV over IP over my LAN, for example, with the N2000 JPEG series?
Okay, I might have to ask you, that sounds like a very involved question. So can we repeat that, or is that one that they mind taking offline?
Yep, so one, if you want to send an email to Thomas, his information is up on the page right now, and it sounds like he'd be happy to help you with that. We've had a couple of people write in asking if you would be willing to submit the PDF of this so that people could have a copy of it.
Absolutely.
Okay, perfect. If you want to send that over to me, I will send that out to everybody who registered for this webinar. So just check your junk mail, everyone. It'll be coming from my personal email from Harmon, and sometimes it gets caught in the junk mail or spam. So just check for that.
So by PDF, we just mean the slide presentation. Would you like my notes as well? And then, or just a PDF of the slides? But I'm glad to send either.
Well, they'll have access to the recording for this
Perfect.
presentation as well. Yeah.
Okay.
So thank you. It looks like that's it that came in for the questions. So as mentioned, if you want to reach out to Thomas directly, his information is up on the screen. The recording for this will be submitted in about 3 days out on our brand playlists out on YouTube. And if you're interested in attending any of the upcoming learning sessions, the calendar is out on pro.harmon.com. So thanks so much, Thomas. We really appreciate it. And thank you, everyone, for your time today. Have a great day.
Thank you.
Thanks. Bye, Thomas.